Right now, more than 24 billion kilometers from Earth, a machine built when home computers were still a novelty is listening to something no spacecraft was ever designed to hear. Voyager 1 is moving through interstellar space, beyond the protective bubble blown by our sun, carrying instruments assembled in the 1970s and running on a power supply that weakens every year. Its transmitter is so faint that by the time the signal reaches Earth, the power arriving at our antennas is measured in fractions so small they barely seem physical. Yet buried inside that whisper is another whisper, a narrow, almost continuous tone coming from the plasma between the stars. Not a message, not a voice, not evidence of aliens. Something stranger scientifically. The tone is so weak that researchers had to filter years of data to pull it out of the background. It changes pitch. It follows variations in the density of interstellar matter. It persists between the violent shock waves that scientists already knew how to explain. And the exact physical process producing it is still not settled. Picture a dark ocean with only a few atoms scattered through a volume the size of your living room. Now imagine those particles behaving like a vast, invisible instrument, vibrating around a spacecraft smaller than a school bus. Voyager 1 is not recording sound in the ordinary sense. Space is far too empty for that. It is measuring electrical oscillations, then translating their frequencies into data we can interpret. Almost nobody outside the field realizes what this means. Voyager has not simply crossed a boundary. It has become the first moving microphone inside an environment humanity had previously studied only from the outside. And the tone it found may reveal the texture of the space surrounding our entire solar system. Stay with me, because by the time this is over, you will never think about the silence between the stars the same way again. Before we go deeper, subscribe and turn on notifications. Missions like Voyager prove that the most important discoveries often arrive long after everyone assumes the story is finished. Let's go back to the beginning. On September 5, 1977, Voyager 1 launched from Cape Canaveral aboard a Titan III Centaur rocket. Its original assignment was ambitious but clear: fly past Jupiter, then Saturn, return close-up measurements and images, and survive long enough to complete the planetary encounters. No one launching it that morning could reasonably promise that the spacecraft would still be operating nearly half a century later. Voyager 1 was built around an opportunity that appears only once every 176 years, when the outer planets line up in a way that allows a spacecraft to use one world's gravity to bend and accelerate its path toward the next. Engineers called the broader concept the Grand Tour. Voyager 1 would take the faster route, passing Jupiter in 1979 and Saturn in 1980. The expectations were planetary. The reality became interstellar. At Jupiter, Voyager 1 returned detailed views of violent storms, delicate rings, and moons that seemed impossible. It helped reveal active volcanoes on Io, the first active volcanism discovered beyond Earth. At Saturn, it examined the planet's rings and atmosphere and made a close pass of Titan, whose thick, nitrogen-rich atmosphere was already one of the great mysteries of the solar system. That Titan encounter changed Voyager 1's trajectory. The gravity assist tilted the spacecraft out of the plane where most planets orbit. There would be no Uranus, no Neptune. Instead, Voyager 1 was thrown upward and outward on a path that would never return. After the main mission ended, NASA did not switch it off. The spacecraft still had working instruments, a functioning radio, and enough nuclear-generated electricity to continue. So the mission was extended. The planetary explorer became a boundary explorer. And here is where the first twist arrives. Scientists knew the sun does not end at the visible surface. It pours out a stream of charged particles called the solar wind. That wind expands in every direction, carrying the sun's magnetic field with it and inflating an enormous bubble around the solar system called the heliosphere. Inside that bubble, conditions are dominated by our star. Outside it lies the interstellar medium: thin gas, charged particles, dust, magnetic fields, and cosmic rays occupying the space between stars. The boundary between the two is called the heliopause. Voyager 1 approached it slowly in human terms and quickly in cosmic terms, traveling about 17 kilometers every second. In December 2004, at roughly 94 astronomical units from the Sun, it crossed the termination shock. 1 astronomical unit is the average distance from Earth to the Sun. The termination shock is the region where the solar wind, racing outward faster than the local speed of sound, abruptly slows as it begins pressing against the interstellar medium. Scientists expected a boundary sequence: fast solar wind, slowed solar wind, turbulent heliosheath, then a crossing into interstellar space marked by several recognizable changes. Some of those changes appeared, others did not. In 2012, Voyager's particle instruments began reporting dramatic shifts. Charged particles associated with the Sun dropped sharply. Galactic cosmic rays, high-energy particles arriving from beyond the heliosphere, increased. The spacecraft appeared to have reached the edge. Then, the magnetic field refused to cooperate. Many researchers expected the field direction to rotate clearly when Voyager crossed from the Sun's magnetic domain into the interstellar magnetic field. Instead, the direction changed far less than anticipated. It was as though a ship had sailed from one ocean into another. The water chemistry had changed, the currents had changed, the wildlife had changed, but the compass still pointed almost the same way. That contradiction mattered. Had Voyager crossed the heliopause, or had it entered a strange transitional region still connected to the Sun? Was the boundary sharp, layered, porous, or folded? Were the models wrong, or were the instruments seeing a temporary event? For months, scientists debated the answer. Voyager 1 had another problem. Its dedicated plasma science instrument, designed to measure the charged solar wind directly, had failed in 1980. The spacecraft was entering the most important plasma environment of its life without the instrument that would have provided the most straightforward confirmation. But another instrument was still alive. The Plasma Wave Subsystem used two long antennas extending behind the spacecraft. It did not need to scoop up plasma like a physical container. Instead, it measured voltage differences caused by waves in the surrounding charged particles. When electrons in a plasma oscillate, the frequency of that oscillation depends on electron density. Higher density produces a higher characteristic frequency. In plain language, the plasma rings at a pitch that tells scientists how crowded the electrons are. And in April 2013, Voyager heard the evidence everyone had been waiting for. A major solar eruption had occurred more than a year earlier. The disturbance traveled outward through the solar system, crossing billions of kilometers before reaching the region around Voyager. When that shock passed through the interstellar plasma, it made the electrons oscillate. The Plasma Wave Subsystem detected the resulting tone. The measured frequency indicated a plasma density far higher than the typical density inside the heliosphere. That was the missing clue. By working backward through the data, the team concluded that Voyager 1 had crossed the heliopause on August 25, 2012, at about 122 astronomical units from the Sun. NASA announced the conclusion in September 2013. The mission had become the first human-made object to enter interstellar space, although it remained gravitationally within the much larger solar system, and will remain so for thousands of years. Stop and sit with that. A spacecraft launched to study Jupiter and Saturn had used a plasma vibration, triggered by an eruption from the Sun, to prove that it had crossed beyond the Sun's protective particle bubble. The Sun itself had struck the bell. Voyager heard it ring. But none of that prepared researchers for the next discovery. The first interstellar plasma events were dramatic but irregular. Shock waves from solar eruptions would eventually reach Voyager's neighborhood, compress the plasma, and produce strong oscillations. In the data, these appeared as whistle-like features. They were scientifically valuable because their frequency revealed electron density, but they did not happen continuously. This is where Stella Oker, then a doctoral researcher at Cornell University, enters the story. Oker and her colleagues examined archival data from Voyager 1's Plasma Wave Subsystem. They were not looking for another loud, shock-driven event. They were searching close to the instrument's noise floor, where weak signals can disappear into the electronic background. And there it was. Beginning around 2017, a thin, narrowband emission persisted through the data. Narrowband means most of its energy was concentrated in a very small range of frequencies. Instead of appearing as an occasional loud whistle, it behaved more like a nearly continuous hum. It was barely louder than noise, but it moved. Its frequency drifted upward and downward in a way that tracked changes in the plasma density inferred from the stronger shock events. When a loud oscillation appeared, the faint line often shifted with it. That correlation suggested the weak emission was responding to the same underlying property of the environment. In 2021, Oker, James Cordes, Shami Chatterjee, Donald Gurnett, William Kurth, and Stephen Spangler reported the detection in Nature Astronomy. Their analysis described a persistent, weak plasma wave emission that allowed Voyager 1 to sample density across roughly 10 astronomical units, with an average spacing of about 0.03 astronomical units, far more continuously than the rare shock events allowed. Now the story gets stranger. Scientists could see what the signal was useful for. They could not say with certainty what was physically generating it. That distinction is crucial. The detection is real. The correlation with plasma density is real. The ability to use the frequency as a tracer is supported by the data. The unresolved part is the exact mechanism that keeps the weak emission going. One possibility is that the plasma is producing thermally excited oscillations. Every plasma contains particles with thermal motion. Even in an extremely thin medium, electrons move, interact with fields, and can support collective behavior. Under the right conditions, that thermal activity may generate a faint background at or near the plasma's natural frequency. Another possibility is quasi-thermal noise. That phrase sounds like instrument static, but it can describe real electrical fluctuations produced by particles around an antenna. A spacecraft antenna immersed in plasma interacts with the surrounding charged environment. The resulting spectrum can reveal temperature and density. There may also be effects involving energetic electrons, weak instabilities, or processes not fully captured by simple models of the local interstellar medium. The researchers did not claim a supernatural mystery. They did something more valuable. They identified a reproducible signal, showed what it tracks, listed plausible physical explanations, and admitted that more evidence is needed to choose among them. That is what "scientists can't explain" means here. It does not mean science has failed. It means nature has provided a measurement before providing a complete mechanism. And that happens more often than headlines suggest. Voyager's hum belongs to that tradition. The signal is not merely an oddity. It exposes the texture of the environment surrounding the heliosphere. Earlier, strong plasma oscillations had already indicated that electron density outside the heliopause was much greater than within the outer heliosphere. Auker's analysis showed that the density measured around Voyager rose substantially after the crossing and then remained within a broadly similar range, with smaller fluctuations, across the analyzed data ending in early 2020. NASA described the rise from 2013 to around mid-2015 as roughly 40-fold. That does not mean interstellar space is crowded, yet density is relative. A nearly empty region can still be much denser than another nearly empty region. And those differences matter because they affect pressure, magnetic fields, shock propagation, cosmic rays, and the shape of the heliosphere itself. Here is the second major finding. The interstellar medium is not a passive void waiting between stars. It is a dynamic plasma. Plasma is sometimes called the fourth state of matter. If you have never heard that phrase before, picture a gas heated or energized enough that electrons separate from atoms, leaving a mixture of charged particles. Because those particles carry charge, they respond collectively to electric and magnetic fields. They form waves. They support currents. They can be compressed, stirred, and shocked. Most visible matter in the universe exists as plasma. Voyager is moving through that medium while still feeling disturbances launched by the Sun years earlier. Think about what that means. Crossing the heliopause did not cut Voyager off from solar events. The Sun's explosions continue to send pressure waves outward. These waves travel across the heliosphere, cross or deform the boundary, and propagate into the very local interstellar medium. By the time they reach Voyager, the eruption that created them may be a distant entry in an old space weather archive. The solar system leaves an aftershock beyond its own bubble. Not a metaphor, not poetic license, a physical pressure front. So Voyager is not simply measuring the space between stars in isolation. It is measuring the interaction zone between a moving star, its magnetic bubble, and the galactic environment through which that bubble travels. Voyager 1 samples only one path. That limitation is easy to miss. The spacecraft is not orbiting the heliosphere. It cannot turn around and compare different regions. It moves along a single outward trajectory, like a needle passing through an enormous, shifting weather system. Voyager 2 crossed the heliopause in a different direction on November 5, 2018, at about 119 astronomical units. Unlike Voyager 1, it still had a functioning plasma instrument at the crossing, providing a second direct view of the boundary. The two crossings showed similarities, but also differences, reinforcing the idea that the heliopause is shaped by direction, solar cycle, and local conditions, rather than being a perfect sphere. Two paths are better than one. But two paths through a structure billions of kilometers wide are still almost nothing. This is why the faint persistent emission matters so much. Every additional density measurement along Voyager 1's route adds detail to a map humanity cannot currently obtain any other way. Here is where the third twist arrives. The signal reveals not just average density, but fluctuations. Those fluctuations may be fingerprints of turbulence. Turbulence is what happens when a flowing medium develops irregular motion across many scales. You see it in smoke curling above a candle, cream folding into coffee, clouds rolling through an atmosphere, and rapids breaking around rocks. In plasma, turbulence can involve intertwined variations in velocity, density, and magnetic fields. The local interstellar medium is far too thin to see with your eyes, but Voyager can detect the electrical consequences of its structure. The 2021 Nature Astronomy study reported density variations on astronomical unit scales between the stronger, shock-driven events. That means the space outside the heliosphere contains measurable texture over distances comparable to the scale of planetary orbits. Picture driving across a desert at night with no headlights, no road signs, and no horizon. The only clue to the landscape comes from the vibration in your steering wheel. A smooth tone suggests flat ground. A changing tone reveals ridges, gravel, and slopes. Voyager's plasma tone is a little like that. The spacecraft cannot photograph interstellar density. It feels the electrical landscape and radios the vibration home. Why does turbulence matter? Voyager is not inside a star-forming cloud. It is in the very local interstellar medium surrounding the heliosphere. But the physics operating there connects to a much larger cosmic system. Every star moves through an environment. Every stellar wind pushes against surrounding material. Every planetary system is embedded in a galactic neighborhood. Our sun is no exception. And here's the part that stops being abstract and starts being personal. The heliosphere is part of your environment. You do not feel it when you wake up. You cannot see its boundary from Earth. But every second, the sun's magnetic bubble helps alter the population of high-energy galactic cosmic rays reaching the inner solar system. Cosmic rays are mostly atomic nuclei accelerated to extreme energies by violent processes in the galaxy. When they strike Earth's atmosphere, they create showers of secondary particles. Some reach the ground, some pass through your body. You are being crossed by particles from space right now. Earth's atmosphere and magnetic field provide major protection. The heliosphere adds another layer of modulation, especially for lower-energy galactic cosmic rays, whose paths are influenced by the solar wind and magnetic field. The boundary Voyager crossed is therefore not just a distant landmark. It is the outer edge of a system that helps define the radiation environment around every planet, moon, spacecraft, and human being near the sun. Now imagine the sun traveling through a denser interstellar cloud. The pressure outside the heliosphere could increase. The heliosphere could contract. The balance of particles reaching the inner solar system could change. Researchers study past variations in the galactic environment, partly because changes in the heliosphere may affect planetary radiation conditions over very long timescales. That does not mean Voyager has discovered an immediate threat. It has not. There is no evidence in this signal of an approaching cloud about to crush the heliosphere. There is no alien transmission. There is no countdown to catastrophe. The personal relevance is quieter and more profound. Your planet exists inside a moving magnetic shelter, and Voyager is measuring the weather just beyond its walls. The faint tone helps scientists estimate density. Density helps constrain pressure. Pressure helps shape models of the heliosphere. Those models help researchers understand how cosmic radiation is filtered as the sun moves through the galaxy. A vibration around a 1977 spacecraft becomes part of the story of why Earth's space environment is the way it is. But none of this is happening under ideal conditions. Now let's talk about what is happening right now. Voyager 1 is aging. Its electrical power comes from radioisotope thermoelectric generators, which convert heat from the natural decay of plutonium-238 into electricity. That power output declines over time. Instruments and heaters must be managed carefully. Every watt matters. In November 2023, Voyager 1 stopped returning readable science and engineering data, even though controllers could tell that it was still receiving commands. Engineers traced the problem to a failed memory chip in the flight data subsystem, the computer responsible for packaging information for transmission. They could not replace the chip. They could not send a technician. They had to rewrite and relocate pieces of software inside a computer operating more than 15 billion miles away, with radio commands taking roughly 22.5 hours to reach the spacecraft, and the response taking another 22.5 hours to return at that time. One attempt. Then, nearly 2 days before full confirmation. The team divided the affected code, stored portions in different available locations, and adjusted references so the separated pieces could still function together. In April 2024, Voyager 1 returned usable engineering data again. Science data followed. That recovery was not magic, it was engineering archaeology. People working today had to reason through hardware designed before many of them were born, using documentation, old code, institutional memory, and disciplined testing. A single wrong command could have made the situation worse, yet the spacecraft returned, still transmitting, still measuring, still listening. The power decline, however, cannot be repaired. To keep the mission alive, the team has been shutting down instruments according to plans developed years in advance. On April 17, 2026, JPL engineers turned off Voyager 1's low-energy charged particles experiment. The instrument had operated almost continuously since 1977, measuring ions, electrons, and cosmic rays, and contributing to the exploration of the heliosphere and interstellar medium. NASA said the shutdown was necessary to conserve power and extend the mission. 7 of the original 10 instrument sets on each Voyager had been shut down by that point. The loss is painful because every instrument is irreplaceable. There is no spare Voyager waiting at the heliopause. No servicing mission is on the way. No modern probe will reach the same region next year, or the year after that. The remaining instruments must carry the story as long as power, temperature, communications, and aging electronics allow. And the Plasma Wave Subsystem is especially important because its strange, weak emission may continue tracing density even when the dramatic shock-driven oscillations are absent. But there is a ticking clock. The spacecraft's power will continue to decline. More systems will eventually be turned off. At some point, Voyager 1 will no longer be able to collect science or communicate with Earth. Engineers cannot give a perfectly fixed final date because the outcome depends on hardware behavior, power margins, thermal conditions, and operational choices. What is locked in is the direction of time. Less power next year, fewer options after that, more distance every day. Voyager's radio beam continues to spread as it crosses space. Earth's deep space network must detect an unimaginably faint carrier and separate it from noise. The spacecraft has no idea that it is famous. It simply follows commands, measures voltages, packages bits, points its antenna toward a pale star behind it, and waits. Meanwhile, the persistent plasma emission raises questions that Voyager alone may not be able to finish answering. Is the signal dominated by thermally excited plasma oscillations? Is it quasi-thermal noise measured by the antennas? How do local particle distributions, magnetic fields, shocks, and turbulence control its intensity? Will the emission persist as Voyager moves into new density regions? Could a future interstellar probe carry instruments designed specifically to exploit this phenomenon? The 2021 research made the uncertainty explicit. New Voyager observations or measurements from a future interstellar mission may be needed to clarify the mechanism. That is the urgency. Not that something is hunting Voyager, not that the signal is dangerous, that the only instrument presently sampling this path may go silent before the mystery is fully resolved. Science has a narrow window in which a nearly 50-year-old machine can keep touching the interstellar medium and telling us what it feels. Here is what I want you to take away from all of this. The universe does not owe us clean boundaries. We expected the heliopause to announce itself with every predicted signature. It did not. We expected useful density measurements to arrive mainly through rare, solar-driven shocks. Then a weaker, persistent tone appeared between them. We expected a mission measured in years. It became a mission measured across generations. Again and again, Voyager has found that the edge is not a line, it is a conversation. The solar wind pushes outward. Interstellar plasma pushes back. Magnetic fields bend and drape. Cosmic rays enter and scatter. Solar eruptions send pressure fronts beyond the heliosphere. A tiny spacecraft passes through all of it, converting invisible electrical motion into numbers that cross billions of kilometers and appear on screens on Earth. The repeatable line is this: the silence between stars is not empty. It has a pulse. That pulse is not alive in the biological sense. It does not think. It does not speak. But it carries information about density, turbulence, pressure, and the environment in which our solar system travels. And perhaps that is the most haunting part. Voyager 1 was designed by human hands, launched by a chemical rocket, guided past giant planets, and sent into a darkness no one had directly sampled. Decades later, it found a tone so faint that it had been hiding beneath the louder events in its own data. The discovery did not arrive with an explosion. It arrived as a line on a spectrum, a nearly single tone, a whisper below a whisper. Subscribe for more factual deep space investigations and turn on notifications so you do not miss the next one. In the comments, tell me which explanation you think future data will favor: thermally excited plasma oscillations, quasi-thermal noise, or a mechanism we have not fully modeled yet. Share this with someone who still thinks interstellar space is simply empty darkness. Far beyond the planets, Voyager 1 continues through that dark ocean, smaller than a school bus, powered by fading heat, carrying the memory of Earth behind a golden cover. Around it, particles too sparse to see tremble in electric fields. The pitch shifts, the density changes, the silence rings. And for as long as the spacecraft can still point home, humanity is listening. Thanks for watching.